A river ends here. It spreads across the floor of Jezero Crater in a broad fan of stone. Branches split apart, curve outward, and fade into layers of sediment that have remained undisturbed for billions of years. From orbit, the shape is unmistakable. On the ground, every ridge and every inclined layer follows a pattern that rivers on Earth have carved countless times before. There is only one problem. Modern Mars cannot sustain a river like this. Its atmosphere is too thin. Its surface is too cold. Liquid water exposed today would quickly freeze or boil away. Yet the landscape below preserves the unmistakable geometry of flowing water ending in a lake that no longer exists. Everything that follows begins with this contradiction. If this structure is truly a river delta, then the world that created it cannot have resembled the Mars we see today. Somewhere inside these silent layers is physical evidence of a completely different planet. The task is not to imagine what Mars might have been. It is to reconstruct what the rocks still remember. High above the crater, orbital cameras recorded a fan-shaped deposit extending from the mouth of an ancient valley. Long, branching distributary channels spread outward, exactly as rivers do when they slow down and empty into standing water. The outline was so familiar that the first interpretation seemed almost too simple. Perhaps it only looked like a river. Planetary landscapes can deceive. Wind can sculpt surprising shapes. Lava can leave behind patterns that resemble flowing water. From hundreds of kilometers above the surface, appearance alone could never settle the question. The uncertainty remained until another observer arrived. NASA's Perseverance rover rolled across the floor of Jezero Crater and turned its cameras toward an isolated rocky outcrop known as Kodiak Butte. Instead of a featureless cliff, the rover found orderly layers stacked one above another. Flat sediment rested above beds that sloped downward at a consistent angle before disappearing beneath younger deposits. The arrangement was immediately familiar. On Earth, rivers entering calm lakes build exactly this sequence. Sediment settles first in deeper water, then advances outward as the river continues delivering sand, silt, and gravel over long periods of time. Geologists describe these as top-set and foreset beds. They are not random layers. They are the preserved architecture of a growing river delta. The rocks carried another clue. Minerals rich in clays and carbonates were embedded within these sedimentary layers. Those minerals form through repeated interaction between rock and liquid water. They do not emerge from wind, sculpting loose dust across a frozen desert. Now, two completely independent lines of evidence pointed to the same conclusion. From orbit, the crater displayed the geometry of a river delta. On the ground, the stone preserved the internal structure expected from long-lived sediment carried into a lake. The simplest explanation could no longer survive. This was not a landscape that merely resembled a river. It was a river. And if one river truly ended here, one question immediately became impossible to ignore. How much of Mars once looked like this? The river inside Jezero Crater no longer stood alone. As orbital maps expanded beyond the crater rim, similar scars began appearing across the ancient southern highlands. Valleys stretched for hundreds of kilometers. Some merged together. Others divided into branching networks that spread across the landscape before ending inside broad, circular basins. They did not point in random directions. They followed gravity, collecting smaller channels into larger ones, with the same organized structure seen in river systems on Earth. One valley could be dismissed as coincidence. Thousands could not. The pattern repeated across the planet. Long drainage networks reached into ancient terrain from every direction. Dry channels converged into basins that once held standing water. entire landscapes preserved the outlines of watersheds, where rainfall or melting water had gathered across vast regions before flowing downhill through interconnected rivers. The map no longer showed isolated features. It showed infrastructure. For a moment, another possibility remained. Perhaps these channels were never part of a lasting water system. A series of violent floods could have carved valleys without requiring a stable environment. Catastrophic events can reshape a landscape in surprisingly little time. But the valleys refuse to behave like the aftermath of isolated disasters. Instead of cutting straight across the surface, they branched repeatedly into smaller tributaries. Narrow channels fed wider ones. Those wider channels emptied into enclosed basins that overflowed into the next valley downstream. The organization resembled drainage networks that develop gradually as water returns to the same landscape again and again. A single flood leaves destruction. A river system leaves order. The evidence continued to accumulate. Ancient lake basins appeared far from Jezero. Sedimentary deposits rested inside them. Minerals altered by repeated contact with liquid water emerged across the same regions. Clays and hydrated rocks appeared wherever the valley networks became most extensive. Each observation came from a different location. Each relied on different instruments, yet they all described the same environment. Water had not visited these places once. It had shaped them. The familiar picture of Mars as a planet marked by scattered accidents quietly collapsed. Jezero was no longer an extraordinary exception preserved by chance. It had become a representative piece of a much larger landscape. The river that ended inside one crater belonged to an interconnected hydrological system that once extended across enormous portions of the planet. The contradiction had expanded beyond the single valley. An entire world now carried the fingerprints of flowing water. Yet every river was silent. Every lake basin stood empty. Every channel ended in dust. If a planetary water system had once existed on this scale, another question now demanded an answer. What could erase an entire world's rivers without erasing the rivers themselves? Every dry river still followed the same path. They wound through valleys, crossed crater rims, and emptied into basins exactly as they always had. The channels remained, the deltas remained, even the fine layers of sediment survived. What had vanished was the one thing every one of those landscapes required: liquid water. The simplest explanation felt familiar because it happens on Earth. Rivers dry up, lakes shrink, water seeps into the ground or evaporates into the air. Desert landscapes preserve ancient shorelines long after the water has disappeared. Perhaps Mars had experienced nothing more than a larger version of that process. The modern planet immediately challenged that idea. Its atmosphere presses against the surface with less than 1% of the pressure at Earth's sea level. Under those conditions, stable liquid water is almost impossible. Exposed water does not linger. It freezes or escapes into vapor before a river can flow across the landscape. The problem was no longer explaining where the rivers had gone. The problem was explaining how they could have existed at all. The river delta inside Jezero had already demonstrated that flowing water remains stable long enough to sort sediment into orderly layers. The global valley networks showed the same stability across enormous distances. Neither observation could be reconciled with the planet that exists today. Something far larger than the rivers had changed. Researchers turned to another record that rivers themselves could not preserve. Ancient impact craters scattered across Mars carry subtle information about the atmosphere that surrounded the planet when they formed. Small incoming rocks burn away differently in thick air than they do in thin air. By comparing the sizes of ancient craters with physical models, scientists reconstructed a world where the atmosphere was far denser than the one surrounding Mars today. Not an exact number, not a perfectly known climate, but consistently dense enough that liquid water could remain stable at the surface. The familiar image of Mars shifted again. This was no longer a frozen desert that had slowly dried out. It was a planet that once possessed environmental conditions fundamentally different from those seen today. Another line of evidence came from the atmosphere itself. Floating above Mars today are water molecules containing two forms of hydrogen. Ordinary hydrogen is light. Deuterium is a heavier version of the same element. Over immense spans of time, lighter hydrogen escapes into space more easily than its heavier counterpart. The atmosphere of modern Mars contains far more deuterium than would be expected if little water had been lost. The lighter hydrogen is largely gone. The heavier version remains behind. It is the chemical fingerprint of enormous loss. That ratio does not reveal precisely how much water once covered Mars. Hidden ice beneath the surface still complicates the calculation. But it delivers a conclusion that does not depend on river valleys or sedimentary rocks. The planet once possessed far more water than it retains today. Now, three independent records pointed toward the same reality. The landscape preserved rivers. Ancient surface conditions allowed those rivers to exist. The atmosphere still carried the signature of losing the water that once fed them. The rivers had not simply disappeared. Mars had lost the conditions required for rivers to survive. One question still remained. What could permanently remove an entire planet's ability to sustain liquid water? One explanation still lingered. Perhaps Mars had suffered a single, catastrophic blow. A giant impact, a violent event that stripped away its atmosphere in one devastating moment, leaving rivers to freeze where they stood. It was an appealing picture. Fast, dramatic, easy to imagine. The planet itself refused to support it. Orbiting spacecraft began measuring something buried deep inside the oldest Martian crust. Vast regions of the southern highlands carried strong magnetic signatures locked into ancient volcanic rock. Today, Mars has no global magnetic field. A compass would not point toward a planetary north the way it does on Earth. Yet these rocks had formed in the presence of one. They had preserved the direction of an invisible shield that no longer exists. The pattern stretched across enormous portions of the oldest terrain. It was not the scar of a single catastrophe. It was the fossil record of a planetary system that had once surrounded the entire world. When those rocks solidified billions of years ago, molten iron deep inside Mars was still moving. That motion generated a global magnetic field. Just as Earth's magnetic field now deflects much of the charged stream constantly flowing from the Sun, ancient Mars once possessed its own planetary protection. Then the record changed. Younger rocks no longer carried that same signature. The invisible shield had vanished. Exactly how quickly the planet's internal dynamo shut down remains uncertain. Current evidence places the transition within a broad span between roughly 4.1 and 3.7 billion years ago. The precise timetable is still being refined. The disappearance itself is not in doubt. The oldest crust remembers a magnetic world. The modern planet does not. For a long time, this remained only a reconstruction built from ancient stone. Then another spacecraft began watching the process unfold in the present. High above Mars, instruments measured streams of charged hydrogen and oxygen escaping into space. These were not computer simulations, they were particles leaving the atmosphere at that very moment, swept away by the continuous flow of the solar wind. The process has never completely stopped. Even today, the sun is still carrying pieces of the Martian atmosphere into space. Slowly, relentlessly, a river delta inside Jezero Crater had opened this investigation. Now every surviving clue pointed toward the same sequence. A small planet cooled faster than Earth. As its interior lost heat, the churning motion that powered its global magnetic field gradually ceased. Without that invisible shield, the upper atmosphere became increasingly exposed to the solar wind. Over immense spans of time, atmospheric gases escaped into space, surface pressure fell, temperatures and pressure crossed the threshold, where stable liquid water could no longer persist. The rivers did not disappear first. The planet lost the ability to support them. No single afternoon ended the habitable Mars recorded inside Jezero Crater. The evidence preserved instead a chain of interconnected failures, each making the next one unavoidable. Only one place remained to test whether this reconstruction could explain everything. The river where the investigation began. The river has not changed. Its channels still spread across the floor of Jezero Crater. The fan-shaped delta still reaches into the basin exactly as it did billions of years ago. The tilted sedimentary layers inside Kodiak Butte remain locked in stone. Nothing about the landscape has moved. Everything about what it means has. At the beginning of this investigation, the delta answered only one question. Did flowing water once exist here? Now it answers a very different one. What does an entire planet leave behind after it loses the systems that made flowing water possible? The rock layers still record a river entering a quiet lake. Beyond the crater, valley networks still connect distant watersheds across the ancient southern highlands. The atmosphere still carries an unusually high proportion of heavy hydrogen, preserving the chemical signature of immense water loss. The oldest crust still remembers a magnetic field that no longer surrounds the planet. Above it all, particles continue escaping into space under the pressure of the solar wind. None of these observations depends on the others. Each was discovered independently. Each survives its own tests. Yet every one now points toward the same reconstruction. The river formed while Mars possessed stable surface water. Stable surface water required a thicker atmosphere. That atmosphere endured while the planet remained protected by a global magnetic field. As that protection disappeared, the atmosphere gradually escaped into space. As atmospheric pressure declined, liquid water could no longer remain stable. The rivers stopped flowing. The delta remained. That sequence does not answer every remaining scientific question. Researchers continue refining how dense the ancient atmosphere once was. They continue debating whether early Mars was broadly warm or remained mostly cold beneath extensive ice. They continue narrowing the timing of the planet's internal cooling. Those uncertainties change the details. They do not overturn the chain preserved by the evidence. The delta inside Jezero Crater never claimed that Mars looked like Earth. It never recorded forests, oceans, or a tropical world. It recorded something simpler. For a long enough period, liquid water repeatedly carried sediment into a standing lake. That single fact requires a planetary environment fundamentally different from the one that exists today. The landscape that first appeared to be an impossible curiosity has become something far more consequential. It is no longer simply the remains of an ancient river. It is the surviving forensic record of a world that progressively lost the atmosphere, climate, and planetary protection required to remain habitable. Billions of years later, the river still points toward the basin where it once ended. The water is gone. The evidence is not